Welcome to The Explainer. Today, we're going to look at the air around us from a pilot's perspective. Because to them, all this empty space is really an invisible ocean, and it's the very thing that makes flight possible.
So let's just dive right in. The space all around you right now, it feels like nothing's there, right? But for an airplane, that nothing is absolutely everything. So let's start with a really basic question. Is it actually empty?
Not even close. You know, the source material puts it perfectly. Air has mass, and when that mass gets moving, it carries an incredible amount of kinetic energy. I mean, just think about it. It's a physical substance powerful enough to lift a 400-ton jetliner off the ground, but it's also powerful enough to cause the sheer devastation of a tornado.
To really get how aircraft use it, you have to stop thinking of air as, well, air. You have to start thinking of it as a fluid. Yeah, just like water. It flows, it swirls, it can be pushed around. And that fluid nature is exactly what a wing digs into to generate the force of lift.
And here is the fundamental rule of how that fluid moves. It always flows from an area of high pressure to an area of low pressure. No exceptions. The analogy from the source is just perfect. If you squeeze the tube of toothpaste in the middle, where does the paste go? To the ends where there's less pressure. Air works the exact same way.
All right, so if air is a substance, what are its key properties? For any pilot, this whole invisible ocean really comes down to three critical characteristics. Let's meet them.
First up, you've got static pressure. This is literally the weight of the entire column of air stretching from wherever you are all the way up to the edge of space, just pressing down. It's pushing on an airplane from every single direction at once.
Next is temperature, and it's way more than just hot or cold. In physics, temperature is a direct measurement of the energy of all those little air molecules. The faster they're buzzing around and bumping into each other, the higher the temperature. It's all about that energy.
And finally, we have density. The easiest way to think about this is just how crowded the air is with molecules. Are they packed in there shoulder to shoulder, or are they really spread out? And for a pilot, this one is probably the most important property of all when it comes to generating lift.
Now, here's the kicker. These three things, pressure, temperature, and density, they aren't independent. They are all tied together in a relationship we call the ideal gas law. All you need to know is that density goes up when pressure goes up, but it goes down when temperature goes up. For a pilot, this isn't some textbook theory. It means a hot summer day or a high-altitude airport directly and immediately impacts how that plane is going to perform.
Okay, so we've got our big three properties. Now let's see what happens to them as an airplane actually climbs up through this atmospheric ocean.
As you climb, pressure and temperature do very different things. The pressure just drops off in this nice, smooth, predictable curve. It makes sense, right? There's just less air above you pushing down. But temperature is weird. It gets colder and colder, sure, but only up to around 36,000 feet. Then, as you enter the stratosphere, it just stops. It holds steady for a while, which is kind of surprising.
So this sets up a kind of battle. The colder temperatures are trying to make the air denser, right? But the falling pressure is trying to make it thinner. So who wins? Well, it's not even a fair fight. The drop in pressure is so massive that it completely overpowers the cooling effect. The pressure drop always wins.
And that creates the #1 challenge for flying at high altitudes. Lower density means fewer air molecules for the wings to grab onto, and fewer molecules for the engines to breathe. So to generate the exact same amount of lift, the plane has to fly faster. It has to force the same mass of air over its wings every second.
So this brings us to a huge problem. The real atmosphere is messy. It's chaotic. It's different every single day in every single place on Earth. For aviation to even work safely, we needed a reliable map of this invisible world.
I mean, that's the core problem, isn't it? If the air over Texas today is totally different from the air over Siberia tomorrow, how on earth can you design a plane that performs predictably? How can a pilot in one country and an air traffic controller in another be sure their instruments are telling them the same story?
The solution is just brilliant. It's called the International Standard Atmosphere, or ISA. Now listen carefully. It is not the real atmosphere. It's a universally agreed upon, totally idealized model that everyone in aviation uses as a common ruler, a fixed benchmark.
The ISA model works by creating a universal starting line. It defines the exact values for a standard day at mean sea level. On this perfect imaginary day, the temperature is a mild 15 degrees Celsius and the pressure is exactly 1013.25 hectopascals. This becomes ground zero for all of aviation.
And it doesn't stop there. The ISA model also defines a standard lapse rate. That's the exact rate the temperature is supposed to decrease as you climb. It's set at 1.98 degrees Celsius for every 1,000 feet, all the way up until it hits that flatline point we saw earlier.
So why? Why is this imaginary perfect atmosphere so incredibly critical for every single real-world flight that takes off?
Well, it does two absolutely vital things. First, calibration. It makes sure every altimeter in every airplane is using the exact same starting point. This is a huge deal for safety, so when a pilot says they're at 30,000 feet, everyone knows precisely what that means. And second, comparison. It lets engineers fairly test and compare the performance of different planes. Without it, you'd never know if one plane was actually better or if it just got lucky and flew on a day with denser air.
So when a pilot sets their altimeter to this standard, they're setting that baseline pressure. In most of the world, that magic number is 1013.25 hectopascals.
But if you're flying in North America, you'll hear a different number. You'll hear about 30 inches of mercury, or to be precise, 29.92. Don't worry, it's the exact same standard pressure, just measured with a different yardstick.
And that right there, that's the whole ball game. The ISA was never meant to be the real atmosphere. It's the perfect, unchanging ruler that allows everyone in aviation to measure, navigate, and communicate clearly inside the chaotic, ever-changing, real atmosphere.
And that leaves us with a pretty cool final thought. We've just seen how a completely invisible, made-up standard is absolutely essential for us to safely navigate our physical world. It kind of makes you wonder, what other invisible standards are out there, quietly holding our complex world together?